Yes. Good afternoon, everybody. Packing 50 years of history in 30 minutes is a difficult exercise. And there's always the danger that one tries to speak about everything. I hope I succeed in finding a good balance between speaking about as much as possible, but I hope I won't, I hope I will stay well within these 30 minutes allocated to me. So rather than going from space down, my presentation is organized the other way around. I'm going up, out of the atmosphere and into space. So, well, in fact, this background picture is a very nice one, which illustrates the structure of the atmosphere. And gravity is something that plays an important role, clearly, and creates a layering in the atmosphere, going from a dense atmosphere up into a very tenuous one, and that's what we call space. What is, from the physical point of view, extremely important there is the collisions that take place between particles. You have a collisional atmosphere below, and then up in space, you've got a collisionless exosphere. The state of matter changes from neutral in the low atmosphere over partially ionized up to a complete plasma in space. And hence we get these different regions. The lower part is typically called the atmosphere for short. Then you have actually the ionosphere and thermosphere sitting at the same place in the middle, where the ionosphere refers to the charged fraction and the thermosphere to the neutral fraction. And then high up, we've got what we call the magnetosphere. And then if you go still farther away, then you go into the interplanetary medium. So space physics is the fundamental science that studies the upper atmospheres of planetary objects and their interactions with interplanetary space. And so there are basically three regions that we study, which is ionospheres, magnetosphere, and interplanetary space itself. There is also an applied science based on this, and that is the science of space weather, which tries to assess or predict the impact of the conditions in space on natural or man-made systems. So let me start with the ionosphere. So, as already mentioned before, the ionization in the ionosphere comes from different sources. First of all, there is the solar ultraviolet radiation, which plays an important role, the major role. But then, especially in the auroral regions, you also may have particle precipitation, that is, particles that come from space and that fall down onto the atmosphere with a certain energy and create additional ionization there. There is also the constant flux of cosmic rays, which are energetic charged particles, which can penetrate down to quite low altitudes. And another source of ionization, very localized in space and time, are meteors. The result of all these ionization mechanisms is that the atmosphere, and the ionosphere in particular, is structured. There is a vertical layering there. Very well known are the D, E, and the F layers, which correspond each to specific ionization mechanisms. This drives a lot of chemistry, as well as was already hinted at. Something quite important also is to remember that when you've got at the same place neutral particles with neutral winds, you have there also these charged particles which move according to different laws. They are controlled by electric fields and magnetic fields, and those two motions do not necessarily have to coincide, so you can have a relative ion-neutral drift, which can create additional collisions, which may be an additional source of heat there locally. All of this may result in outflow of ions and electrons out of the atmosphere upward, and this also is responsible for emission, airglow, or auroral emission. So there are very strong diurnal and local variations in the ionization content of the ionosphere, and in fact only this F layer survives the recombination during the night. A very important consequence for this is that, of course, ionization is proportional to conductivity in the atmosphere. So changing degree of ionization means changing electrical properties of this ionosphere, and that's quite important. I just want to highlight, for instance, that figure there below, which shows the conductivity in the ionosphere as seen from above. And so you see on the day side, which is the 12 o'clock, is noon on top, there is a certain degree of ionization, It's much darker blue on the night side, so there is much less charges present in the ionosphere. Then you see there clearly this ring-like shape, which is related to the aurora. Aurora create particle precipitation, which enhances very locally, but often very dramatically, the local conductivity. Marcel Nicolet started much of this work on ionospheric ionization and its impact on atmospheric chemistry. And this work prompted, for instance, the operation of the ionosonde in Durb. Some ionospheric research has been done at the Institute by Kokkarts in Wissenberg in the 60s and 70s. But most of the Institute's work does not really focus on the ionosphere as such, but on its coupling with the magnetosphere, which is located above. Indeed, charged particles, ions and electrons, they can move quite easily along the Earth's magnetic field lines. And therefore, any electric potential difference that you may have somewhere in the magnetosphere will automatically have some imprint on the ionosphere, because it can act as a battery that powers an electric circuit which closes through the ionospheric resistance, and that resistance, of course, is dominated or dictated by the ionospheric conductivity. So with this, you can create potential differences between the ionosphere and the magnetosphere. For one sense of this potential difference, we will have electrons from the magnetosphere that will be precipitating downward, and that's the situation that you have in typical diffuse aurora or in discrete auroral arcs, like this narrow curtain of light emission that you see here in this picture. For the opposite sense of the potential difference, you may have ions that precipitate, but in particular you will have electrons that move out of the ionosphere up into the magnetosphere, and that can create black aurora, or such structures may also be associated with subauroral ion drifts and other, well, exotic phenomena for the non-initiated, but which are actually quite important from the dynamic point of view. The Institute has contributed a lot of work, especially on the quasi-electrostatic types of magnetosphere-ionosphere coupling and aurora. We have worked on current voltage relation, on the coupled system. We've done Vlasov simulations of the particles on an auroral field line. We've modeled the generator of aurora, tried to interpret observations of discrete aurora of polar cap arcs. We've worked on these subauroral ion drifts. We're doing auroral tomography. There is actually a whole diversity of topics in this field that we've been looking at. But let me highlight a few aspects of that. One of the things that we try to do is to bring together data which are gathered from different sources. For instance, with the 4 cluster spacecraft somewhere out in the magnetosphere, then other spacecraft which fly at low altitude, below the auroral acceleration region, and also ground-based facilities like these ALICE cameras, which are optical cameras looking at aurora, and these IceCat radars, some of those you see in this picture below. So simultaneous images of the same volume of sky can be used to do some sort of 3-dimensional reconstruction of the auroral emission. That's ionospheric tomography, which we do with these ALICE cameras in collaboration with the Institute in Kiruna in Sweden. Then, in terms of modeling, the latest types of modeling that we're doing involves doing Vlasov simulations of what happens along a field line. A Vlasov simulation is basically a very detailed, the most detailed type of simulation that you can do in a plasma, which is basically looking at the particle velocity distribution functions in every point in space and in time. Of course, computational power is what limits you here, so we're doing these computations only along a single field line. And so the result of such computations is that we get an idea of the distribution of this electric potential with altitude. It can also tell us how the densities of the different populations change. And in particular, and that's presented here in these bottom plots, you can analyze in each place where you want, you can analyze the velocity distribution function. And in a sense here, these are plots of vertical velocity versus perpendicular velocity. So vertical meaning velocity along the magnetic field line, perpendicular is perpendicular to the magnetic field line. And you can distinguish different regions in there and identify particles which come from the magnetospheric equator, particles that will precipitate down into the ionosphere, or also trapped particles which may hang somewhere in the middle. In this case, these are electrons which are trapped between the electrostatic double layer, the strong change of potential there, which are trapped between their mirror point and the electrostatic potential difference, in fact. Okay. Then there's this inner magnetosphere. So during the day, solar UV ionization leads to ionospheric upflow. So it leads to ionization, creates this F layer, and that may create an upflow. Well, at low geomagnetic latitude, the plasma that moves out of the ionosphere there clearly stays on closed magnetic field lines, and therefore it forms a reservoir which is called the plasmasphere. During the night, this plasma from the plasmasphere descends back again and keeps the F region alive. These are some pictures which I want to show because they illustrate the type of data that we've been working with. On the right are data, 4 plots you see there, coming from the 4 cluster spacecraft. These are spectrograms. And on each of these spectrograms you see there a line which goes up and down, which is a characteristic frequency of the plasma that is emitted locally, and which is proportional basically to the plasma density, so how many particles there are per cubic centimeter. And this represents actually a path through the plasmasphere going from the southern hemisphere up to the northern hemisphere through what is called a plasmaspheric plume. You see that also in this image picture as this drainage plume. So this is one of the features that we've been examining in detail with cluster data. And I just want to use this as an example to show that we are using both in situ data, some remote sensing data, and also models to try to understand these phenomena. In fact, we've done a lot of plasmaspheric research at the Institute. It was initiated long ago by Joseph Lemaire. First was theoretical work, for instance, predicting the plasmaspheric wind, something that has been confirmed in recent years by cluster. Then we have this observational analysis of plasmaspheric erosion and refilling, and of plasmaspheric plumes. And this observation analysis is only possible if you can put all the data into context, which has been done using dynamic plasmasphere model. And one of the outcomes of this work, recent outcomes, was this book about the Earth's plasmasphere, which is, I think, for the moment still one of the reference works in the field. Also, in this inner magnetosphere, there are the radiation belts mentioned before. They are fed by magnetospheric storms and other mechanisms, and they consist of energetic particles, energetic charged particles that are actually trapped in the Earth's dipole field. They can be fed quite instantaneously on a time scale of minutes to hours, and they get gradually destroyed by several mechanisms over longer time scales, which can go up to months. Radiation belt work at the Institute dates back to the 1980s, in particular in relation to the space weather activities, because this type of radiation is clearly quite harmful to satellites and to humans in space. Most recent advances in this field are the EPT instrument, which was built to a large extent also at our institute in collaboration with Kinetic Space. This collaboration is headed by the Université Catholique de Louvain. So this is an instrument carried on the probe by a vegetation satellite in low altitude polar orbit. And in doing so, it is scanning the low altitude footprint of the radiation belts, which you clearly see in this picture, and you also see there this big blob of the so-called South Atlantic anomaly. Now, if we go farther away from the Earth, well, somewhere we're going to encounter interplanetary space. The interaction between the magnetosphere and interplanetary space, well, that's the region that we call the outer magnetosphere. Now, we know that the sun emits a continuous stream of charged particles called the solar wind. Somewhere that interacts with the Earth's magnetosphere, being the region dominated by the Earth's magnetic field, the Earth's intrinsic magnetic field. And so the supersonic solar wind first passes through a bow shock, which is the place where it becomes subsonic. From that point on, the solar wind feels this magnetic field of the Earth as an obstacle, an essentially impermeable obstacle to the solar wind flow. And in the magnetosheath, the flow will be deviated around this obstacle. Then the interface between the shocked solar wind flow and the magnetosphere itself is called the magnetopause. And as you can see in this sketch, the magnetosphere is compressed on the sunward side by this ram pressure of the solar wind, and it's extended on the night side into a long magnetotail. The structure of the magnetosphere is extremely complicated, and I will not attempt to explain it in the minutes that I have available here. I only want to say that while you may draw such complicated sketch, and that helps in understanding what's going on, one should not forget that this is all very dynamic, because the solar wind and the solar wind pressure changes on timescales from seconds to decennia, and even longer, of course, even on cosmological scales. So, consequently, there's a caveat. Such pictures, they serve some purpose, but you should not push that too far. I will not try to explain this. So a vast body of research on the structure and dynamics of the magnetosphere has been the hallmark of our space physics group, initiated by Joseph Lemaire and Michel Roth. The focus of this work has been on the structure of plasma interfaces, regions, or interfaces separating different regions in the magnetosphere, dynamical plasma transfer processes, how can plasma come from the solar wind into the Earth's magnetosphere, for instance, surface waves on the magnetopause, resonant wave mode conversion, a lot of processes which all have to do with mass and energy transport between the solar wind and the magnetosphere. Much of that work has been done in the context of the cluster mission, and some of us are co-eyes on cluster instruments. And that work has become possible by developing new techniques, new data analysis techniques that allow you to deal with multi-spacecraft measurements. Some of those, for instance, deal with the magnetospheric boundary structure and motion of that boundary. And there's also been a lot of work on plasma turbulence, which then has been followed up on with an FP7 project. And then going beyond the Earth's magnetosphere, well, we have to know the environment in which this magnetosphere is living, and that's the interplanetary medium. Interplanetary medium, or solar wind, is this continuous outflow of magnetized plasma produced by the sun. Now, this is not a constant flow of plasma. There are lots of perturbations there. Perturbations on the sun that are of interest to us are not only those produced by the plasma itself, but first, events that create enhanced UV emission, like flares, solar flares. And then there is this enhanced thermal plasma outflow, which are typically called these big coronal mass ejections, but also enhanced energetic particle fluxes in the form of solar energetic particles. Both the plasma and the field perturbations accompanying these events may have important dynamic consequences in the interplanetary medium, but then also an impact on the Earth's magnetosphere. Much of the work done at the Institute has drawn on experience with ESA's Ulysses mission. That was mostly in the 90s. This was the first mission, and I think still the only space mission which put a spacecraft really out of in an orbital plane, well out of the ecliptic plane. And the work focused both on large-scale structure, like the heliospheric current sheet, sector structure, problem of the origin of the solar wind, and on small-scale structure like the discontinuities and waves present there. Current work includes still looking for this unsolved problem of high coronal temperature and high solar wind speed, studying solar wind turbulence, its effect on the plasma distributions in the solar wind, and the acceleration and propagation of these solar energetic particles. The Earth is not the only object that is immersed in this solar wind. There are also other planetary bodies, of course, and while the focus of our work has been mostly on Earth, primarily because of the fact that we have a wealth of data there, it's clear that studying other planetary bodies can help us in understanding what is really going on, what are really all these physical mechanisms behind what's going on. So briefly to summarize, well, Mercury, has a magnetic field, but it has not much atmosphere, so in that sense it's simpler than the Earth's magnetosphere. Venus and Mars have atmospheres where they do not have a global magnetic field. So there you have a direct interaction between the solar wind and the ionosphere. There is not really a magnetosphere as such. Then you have the gas giants, which all have an intrinsic magnetic field. So in that sense, they have magnetospheres resembling the Earth's one. But they are at the same time different from the Earth because the dipole field direction and orientation is different. And also there are moons present, moons inside this magnetosphere which serve as the source of neutral material in the first place. So that creates a lot of differences. And then ultimately there are of course also these comets, which are very small bodies with minimal gravity, no significant magnetic field, so they cannot even retain their tenuous atmosphere. Still, the same processes as photoionization and so on are taking place there. So focusing there on this comet, because that's a very hot topic these days at the Institute, well, we are involved in the DFMS mass spectrometer on Rosetta. And a comet environment is basically driven by the sun, by sunlight. That's warming up the ices on the surface of a comet, which then evaporate into gas. And so we see there that, for instance, the proportion between CO2 and water released by the comet depends on the solar flux on the comet. It's clearly the amount of CO2 is enhanced when the comet is still rather far away from the sun. While when close to the sun, water evaporation is predominant. The solar EUV flux controls the photochemistry taking place in the comet's atmosphere. And there is, of course, also the solar wind particle impact on the gas, on the dust, and on the surface of the comet, which may lead to radiolysis of certain elements. Yes, and so on Rosetta we have there this pressure sensor and 2 mass spectrometers, and the Institute has been involved in the DFMS mass spectrometer, where together with IMEC and OIP we built the detector electronics. Let me just give you a brief preview of some data. This is the bottom plot here, the big plot, shows as a function of time, it's about a duration of 1 day, and a function of mass, going from 12 atomic mass units to 50 atomic mass units. And the color gives the intensity of the detected signal after calibration. And so basically what our mass spectrometer is doing is, this is a mass spectrometer with a very high mass resolution. So it is looking always at small pieces of the mass spectrum. And so I've just put all the spectra acquired during 1 day together in this one plot. And you see that we are basically scanning the entire mass range piecewise, and doing so we get these vertical stripes. So I want to highlight 4 important aspects here. First, there are 3 intense horizontal lines that you see corresponding to water, CO and CO2, which are the main constituents in the comet's atmosphere. That's one. If you look very closely, then you see that the intensity, and you can see that especially for the water line, the intensity is not constant. In fact, there is a variation there which corresponds to the rotation of this cometary object. And then what I want to draw your attention to also is that in fact you see a bright dot at almost every AMU, meaning that at each integer mass we are seeing something. So there is really a wealth of data, a wealth of different species that are being detected by our spectrometer. And just to give you an idea, I put there this small picture, I hope it is reasonably visible, where we see a few peaks centered around mass 19, where, for instance, the middle peak corresponds to OH, but then not with ordinary oxygen, not with oxygen 16, but with oxygen 18. As you can see, these are very minority constituents, and we can detect and resolve them exquisitely. So there is really a lot of power in these observations. Then there are also meteors in our solar system, and in particular, these meteors may enter the Earth's upper atmosphere. Well, our institute operates BRAMS, the Belgian Radio Meteor Network, which monitors the sky above Belgium. We have a transmitter located, that's a picture down here. It's probably not so easy to see. Basically, it's an antenna consisting of a cross dipole antenna but we put a big reflecting metallic grid underneath to get as much power up in the sky as possible. That's a transmitter located in Durp with our compliments to the Royal Meteorological Institute for letting us have that beacon there. So it is sending out a constant sine wave at a given fixed frequency out above Belgium. And then we have about 25 receivers, simple receivers, scattered over Belgium. There is an interferometer in Humain, thanks to the Royal Observatory there. And we have many of these receiving stations operated at public observatories or by amateur astronomers. And so these receivers record reflections of the signal coming from the transmitter, and they reflect it back to the receiver. So these are reflections of the meteor ionization trail. And that gives spectrograms like these. For instance, the top spectrogram, you see the horizontal line, which is just the beacon signal that you also receive directly. Then you have these S-like curved lines, which are reflections from airplanes. We're not that much interest in airplanes. But what you do see also are these short duration vertical blips, and these are all individual meteors that we detect. And occasionally there is something else, like in this bottom plot, there is this reflection of a huge ionization cloud, which was actually the re-entry of a Soyuz third stage. In collaboration with the Von Karman Institute for Fluid Dynamics, we've started modeling the meteor ablation profile in order to be able to calibrate, so to speak, our Browns system in terms of incoming mass of objects. And that should allow us to create a mass flux model, which is important also in view of space weather. So then I come to this topic, space weather. It's the applied science stemming from space physics. So clearly changes on the sun and in the solar wind and in the magnetosphere may have an impact on Earth or on other planetary bodies. Space weather is a term used to refer to the instantaneous conditions in space, often with the goal of forecasting or nowcasting those conditions so that one may guide operations in space by this. And there is also space climate, which takes a more long-term view and which is typically considered when designing, for instance, shielding for instruments to be put on spacecraft. The range of space weather impacts on man and technology is vast. It goes from danger of single event upsets in the electronics of spacecraft, to degradation of solar panels of spacecraft, to effects on the ionosphere, GPS perturbations because of additional ionization in the ionosphere, but also effects on the ground may be there, geomagnetically induced currents in power systems, in pipelines. You may have radiation doses received by people aboard airplanes flying transpolar routes, and so on and so on. It's really a huge amount of space weather impacts. And the more our society is basing itself on technological systems operating in space, the more vulnerable we will be to space weather. Of course, I don't have to say it, man itself is also an easy target for ionizing radiation, which can create, for instance, DNA damage. Now, one of the primary risks once you're outside the magnetosphere are solar energetic particles. Well, you can see them in these pictures from SOHO, excuse me, where you see a number of coronal mass ejections. But after these coronal mass ejections, you see sometimes this sort of snow appearing on this detector, like here. And that snow is basically, these are hits on the detector of these energetic particles. Of course, in this case, that's not very bad by itself, but if some of these particles hit your electronics, or mission-critical electronics, and knock it out of its good operational order, well, then you're really in trouble. And that's why also at our institute we are working, or we have been working on the generation and propagation of such particles, and we try to incorporate that knowledge into space weather prediction tools, such as the concept tool. Show here a screenshot of this, which is an alert system basically, which was put together in the context of an FP7 project. This expertise is put to use also in the context of ESA's Space Situational Awareness Program. And then since many years, our institute has developed the SPENVIS system for ESA, which is a system providing an environment where you can run engineering models that assess the impact of space weather conditions on, for instance, a spacecraft or an instrument on board the spacecraft. As you can see, many of these services take the form of a web application. And then we also have this Space Situational Awareness Space Weather Coordination Center located at the Space Pole, which is a collaboration of the Royal Observatory and our institute, which is providing the first European space weather help desk. So where you can ask your questions about space weather conditions or space weather services available. How do we do our research? I want to just spend a few words on that. So of course, we need to feed models in our theory with experiments. So clearly, of course, we've been relying on ESA missions to gather data, but progressively our institute and our division is seeking to acquire scientific data by its own means. Ground-based data, well, there we have got this BRAMS network for meteor detection. We also have a VLF antenna installed in Humain, which is giving us data about the plasma sphere, and we've constructed the spectrophotopolarimeter, which will be deployed next month in Scandinavia in conjunction with these ALICE cameras with the goal of measuring polarization of auroral emissions. And then space-based experiments, we've got EPT flying for the moment, we've got the FMS near the comets, and we are building Langmuir probes for the Picasso CubeSat, which you see here, and I think more about Picasso will be said later on today. We're involved in educational activities. Some of us teach at universities. It's important to mention there our role in setting up this Master in Space Studies. We host internships, master theses, PhD theses. We've got a lot of education and public outreach activities like our open doors via the ESRO office, expositions in the planetarium, Redu, elsewhere. And we've also built some very nice demonstration material like this Planetarella, which you can see there. I hope the contrast is good enough. This is basically a vacuum vessel where you put a big potential difference between two electrodes and you see what happens. And in doing so, you can recreate aurora, or let's say emissions which are similar to aurora. I just want to mention some of our funding channels that have helped us throughout the years, and I tried to come up with a list of everybody who contributed to the work of our division, and I hope I didn't forget anybody. Thanks for your attention.